Chapter 8 is a relatively short chapter for us. We're going to take a look at the applications of trig functions that we've talked about earlier. Again, these are sine, cosine, tangent, cotan, secant, and cosecant. Now, in our applications, we are primarily going to be working with sine, cosine, and tangent, although we could set the problems up to where we use the other three trig functions, but the most popular of the six are sine, cosine, and tangent. So I'm going to stay with that norm. Relatively short chapter at that. We only cover 3 sections in this chapter. The sections are the right triangle trig applications, where we view a situation as the setup for a right triangle, and then we try to apply the trig functions to the situation, and that will help us find a measure of sides or lengths, and we can find a measure of angles from one location to another location. Section 2, we take on the law of sines, and section 3, we take up the law of cosines, and then we also look at some applications of those. So let's begin with the right triangle trig application. If you recall, the way I approached the trig function was through a unit circle, and I have my unit circle here. So for now, think about this as a unit circle of radius 1. We define the point with whose coordinates are x, y on the circle. The equation of the circle is x squared plus y squared equals 1. I'll change that later, but for now, let's say it's 1. So we managed to define the trig functions that correspond to the measure of central angle. We called it t, and because the unit circle is radius 1, the arc of the circle, remember s is equal r theta, but r is 1, so s and theta are equal. Therefore, the arc length here is also equal to t. Okay, and then we defined cosine and sine of the central angle t as such, and we went through and created the other 4 trig functions. So that's still correct. What we want to do now is we're going to do what some other textbooks do, is that they introduce these 6 trig functions as measures of the ratio of sides of a right triangle. Okay, now interestingly, based on what I have here, I can actually generalize what I have now, and we can create a right triangle in what I have right now. So let me change all of this. I'm going to remove these. These are still working, but what I want to change is the following. I'm going to change my angle, central angle t to theta, and I'll also want to construct a right triangle here. The radius that was 1, now we're going to allow the radius to be some arbitrary number, positive. There you go, that's the radius. Call it c. Trying to match it against the hypotenuse of this right triangle. Okay, and we can, from the geometry of this triangle, we can see that the one side is adjacent to theta is x, and the side opposite is y. So this is a circle now of radius c. Okay. Now it's interesting, and it's not coincidental that the equation of the circle is now centered at 0, 0, but the radius is r. So this is the equation of that circle. Now, very interesting that the equation of the circle actually matches the Pythagorean theorem as it applies to a right triangle. If you recall from a right triangle, which I have up here, the Pythagorean theorem says that the square of 2 sides is equal to the square of the hypotenuse. So there's a very, very close connection between the equation of a circle and the Pythagorean theorem. And in fact, as you can see, I have created this right triangle here, and from that we can actually come up with the equation of the circle, as well as establish the Pythagorean identity. So everything we've said still works in terms of the 6 trig functions, but what we're going to do is we're going to Think of these now as, instead of ratio of x to y, as the ratio of the sides of a triangle. Okay, and here are the 6 trig functions. So sine theta, which we formally define as, in terms of the coordinates of a point on the unit circle, we defined it as sine was y over c. Well, y is now labeled, or I should say relabeled, as b. So if you look at this triangle, that's like y, and adjacent, which is a, that would be x. So anywhere we had x and y formerly, we can replace them with a's and b's. And there we have. So I'm sure almost all of you have seen this. Again, the only difference is now that we are now introducing the trig functions as a ratio of sides of a triangle, a right triangle. And a right triangle is a triangle that has a 90-degree angle in it. And there you have it. Now, interesting, something about the fact about the right triangle is that the measure of the angles, so let's say I have theta and call this, I don't know, phi. The measure of the two angles, these two angles become complementary in a right triangle. And also remember that since we're talking about triangles now, is that the sum of all angles. So if I label this triangle, let's say label it as B, C, and A, like that. Sum of the angles A plus angle B plus angle C should equal 180 degrees. This is true for any triangle in a Euclidean geometry. In a non-Euclidean geometry, some of the angles could go as high as 360 degrees. But we're looking at plane, flat surface, not a curved surface. In a flat surface geometry, which we call Euclidean geometry in honor of Euclid, the sum of the interior angles should be 180 degrees, which means, again, theta plus, I said theta and I wrote theta twice, theta and phi, these two angles, the measure of these two angles should add up to 90 degrees. So these two angles are what we call complementary angles. Theta and phi become complementary. Now, if you look at in terms of the trig functions, this is something interesting. So, for instance, we have sine theta is the ratio of opposite to hypotenuse, which is b to c. Now, the side that is opposite b becomes adjacent, that's opposite, a little b opposite of capital B. Okay, that's the side. This side, with respect to A, vertex A of that triangle, it becomes adjacent to A, doesn't it? Right, what's opposite to B becomes adjacent to A. I mean, it's opposite theta, sorry. What's opposite of theta becomes now adjacent of phi. Okay, now because of that, B to C with respect to phi, this would be equal to cosine of phi, wouldn't it? Right, the ratio of adjacent to phi to hypotenuse. All right, so that's actually something interesting that exists between an angle and its complement. So it is for this reason that we call sine and cosine cofunctions. Okay, in fact, the co in sine is short for cofunction. Cofunction of sine, that's what that is. Okay, so what is a cofunction then? Let me give you a definition. The cofunction is simply let's call it the trig function of the complement. So it's the trig function of the complement of an angle is called cofunction. Okay, so for instance, if I have cotangent, well, the co in cotangent stands for cofunction of tangent. Cosecant is cofunction of secant. Okay, so that's something, again, that's very interesting that exists between an angle and its complement. Now, if I think in terms of, for instance, tangent of theta, tan of theta is going to be the measure of side opposite to theta over adjacent to theta. That is b to a. Okay, that's the ratio of b to a. Now, with respect to angle phi, the ratio changes from a to b, right? Opposite of phi to adjacent. Well, a to b is going to be now, or if I want to keep it as b to a, tangent of phi would be a to b, but to keep it the same as the one I had earlier, b is adjacent to phi, a is opposite to phi. So this is going to be the same as cotangent of phi. See that? All right, so enough said about that one. Now, because of this cofunction relationship, by the way, we can actually find the exact measures of some of these, well, not exact measure, but we can actually convert from one trig function of an angle to trig function of the other. So for instance, if I want to rewrite sine of 20 as the measure of its cofunction, then that would be cofunction of sine of its complementary angle. And in an example, let's say tangent of 10 degrees will be the same as cotangent of 80 degrees. If I'm looking at cosine of 34 degrees, that would be sine of 56. So whatever those measures are will be exactly the same. Okay. I didn't mean to say exact values, but they have exactly the same measures of the function, an angle and its cofunction. And for instance, let's say I want to do secant of pi over 3. Well, if I need to relate that to cosecant, it will be cofunction of the secant of the complementary angle, right? And here, because pi over 3 is 60, pi over 6 is 30, combined they add to 90 degrees. So in other words, these two angles are cofunctions. Okay. Now, that's pretty much all there is in this section. Let's take a look at some examples here. Okay. And for instance, let's say I want to find, let's do something that we've done with cofunctions here. Let's say I want to find the exact value of this expression without a calculator. I have cosine of 10 degrees, and suppose I have sine of 80 degrees. Now, without using a calculator, I can change cosine of 10 to sine of 80 degrees, right? They're cofunctions. And divide by sine 80, and the whole thing is exactly 1 without using, again, a calculator. Turns out to be kind of handy here. Let's say I have another expression. Let me make up. Suppose I do cosine 35, and then let's do sine of 55. So those two add to 90. Then I'm going to go sine 35, cosine 55. Okay, now for this one, I can change either sine to cosine or cosine to sine. So let me change my sine to cosine here. Then I have cosine 35. Now sine 55 would be the same as cosine of 35 degrees. And I'm changing cosine of 55 to sine on the other side for this term, the second term. And that would be sine of 35 degrees. So in other words, I have cosine squared 35 plus sine squared 35. Correct? And using Pythagorean theorem, cosine squared theta plus sine squared of the same angle theta should be 1. So the answer to this is 1. See how that works? Now I could have done it the other way. I could have changed cosine 35 to sine 55, sine 55 plus sine 35. I'm going to change that to cosine 35 and cosine, not 35. Once we go to cofunction, we have to use the complementary angle, cosine 55. I'm looking at the initial expression. Now I get sine squared 55 degrees plus cosine squared 55 degrees. Again, as long as the measure of the angles are the same, sine squared plus cosine squared should equal to 1. And there you have it. So we got two different Pythagorean identities, if you will. There you go. By converting two cofunctions. All right. Now let's take a look at some interesting application problems. Okay. I'm going to bring this one first. Okay, so this is my first, call it a real life application. Okay, so for this application, we're given this drawing and the dimensions are all given. Okay, see what the question is asking. To support the roof, another beam will be attached to the top of the center beam. See figure. Okay, we're talking about new beam here. All right, to provide support. What's the question? At what angle of elevation is the new beam? In other words, what is the pitch of the roof? Okay, this is the angle of elevation. Now, speaking of angle of elevation and depression, by the way, let me quickly mention that. If you think about, let's say here's an eyeball. Okay, there you go. If you're looking up at an object here, let's say we're looking at the moon, not the sun, because we don't want to look at the sun directly, right? So let's say this is the moon. You're looking up at the moon or any object in the sky. The angle that your line of sight makes with the horizontal, this is the horizontal. Okay, and this is called an angle theta. The angle that your line of sight, and this is your line of sight. The angle that your line of sight makes with the horizontal is called an angle of elevation. Elevation, because you're looking up, you're elevated. The object, actually, not you, but the object is elevated. Now, the same concept, suppose here's the horizontal, and this time this is the eyeball. Okay, and I'm looking down at an object on the ground. Okay, let's say you find something on the ground. Okay, let's say this is a pack of something. And I'm looking down at something. So this is now an angle of depression. The same angle. So if you're looking down at something, your line of sight, the angle the line of sight makes with the horizontal is called angle of depression. Looking up, angle of elevation. Now looking at this one, because you can kind of think of it as going up to a point. So this angle is angle of elevation. All right, so let's say we want to find the angle of elevation here, or the pitch of the roof. So my focus is just going to be on this segment. Okay, and I can kind of do a side view of that structure. If I do a side view, it's going to look something like this. Correct? That would be the side view. And here's what the pitch theta is. Now for the dimensions that I need here, 46 is from the top to the bottom. So this entire distance, this entire side, this whole side is 46 feet. Now of that 46 feet, 20 feet of that is the height of the structure, right? The walls, if you will, the height of the walls on the side. Therefore, this is 20 feet. That means the remaining portion should be 26 feet for the total of 46 feet. That's from the roof to the top. Okay, 26 feet. What else? The other thing that I need to complete my triangle is this. The side here is 10 feet, right? This is given to be 10 feet. So I'm going to project that on my drawing. Cool. And then that's good, because the beams here and this side of the house, they're parallel. We can assume they're parallel, they don't cross unless the wall is crooked. Okay, therefore, this side should be 10 feet. All right, and from this we can simply form a simple trig ratio. I'm going to go tangent of theta for this one, the ratio of opposite, 26 to 10. So I'm looking at this triangle now, 26 to 10, and how do I find the measure of angle theta? I have to go through the inverse tangent by definition of inverse, so that's going to be arctan of 2610. This is not a special angle, so use the calculator, and using a calculator I get 69 degrees. So that will be the pitch of the roof. Okay, again, notice how simple but still very practical, very powerful in helping us solve application problems. Okay, let's do another one. How about here? I've got this one. Well, let's try this example. Okay, I'm gonna leave this one for later. So in this next example, this one involves the Eiffel Tower, the tallest tower built before the era of television masts. The Eiffel Tower was completed on March 31st, 1889. Okay. Now we want to find the height of the Eiffel Tower before the television mast was added to the top using the information. Okay, so what is the information again? Notice how interesting we can kind of view things in terms of a right triangle. We can create our hypothetical right triangles the way we do. Okay, so we want to find the measure of the height, call it h, the height of the tower. We're given the angle of elevation. Theta is 85.361 degrees. And from a distance from the edge of the tower to the center of the base of the tower, that distance adjacent, call it A, is 80 feet. That's adjacent to the angle. All right, so I'm calling this A. And you want to find H again, so very easy. I can do tangent again. So tangent of theta in this case is going to be H opposite to adjacent. That means tangent of 80, tan of 85.361 is equal to H over 80. And then we can cross multiply. This one, I don't even have to use the inverse. I just use 80 times tangent of the angle. And when you do this, by the way, you gotta, of course, make sure your calculators are in degree mode, correct? All right, and 985.91 feet. And there you go. That would be the height of the Eiffel Tower. Okay. Again, not too bad, but it's very powerful. Something very simple and yet so practical. That's amazing. Okay, let's take a look at this example now. You're going to find the speed of a truck. So for this one, let's say the question reads, and let me bring the other part of this question as well. Part of it is left out. All right, so here is the full problem now. This is an interesting exercise, actually. I like this one. And it's very practical. Let's take a look at this. The question reads, a state trooper is hidden 30 feet from a highway. So here's a state trooper. Okay. Something they do well is to hide and catch those who go over the speed limit. 1 second after a truck passes, the angle theta between the highway and the line of observation from the patrol car to the truck is measured. So there we have it. This is the measure of the angle from the patrol car to the truck. Okay, and remember, this distance is fixed. The distance from patrol car is fixed to the road. Okay, in part A, if the measure of the angle measures 15 degrees. So this angle is now 15 degrees for now in part A. How fast is the truck traveling? And we want the answer in feet per second, which is naturally what we're going to get because we got given feet and we got given second here. And then we're going to convert that into familiar miles per hour so we understand it better and can relate to it because that's what shows on our gauges, right? And our speedometer. Now, something interesting here, by the way, we're not given the measure of the side, right? At t equals 0, let's say the truck is here, and t equals 1 second later is here. So we need to know how far that truck has traveled, right? In 1 second. Now, to do that, we need to go back to the formula we had for a moving object, right? Velocity, or in algebra, they call it speed. And we are okay to call it speed also. Speed and velocity are the same in the context we work with. In the next chapter, when we talk about vectors, turns out that velocity has both magnitude, which the magnitude is the speed of the moving object, and it's also a direction. We can associate a direction to velocity. So for example, let's say the truck is going eastbound, so I can represent that velocity vector using a vector with a direction, has magnitude and direction. We'll discuss this in the next chapter. Okay, but for now, I'm going to call velocity, which in algebra, remember they say d equal rt. You probably remember this one from many, many years ago. Many days ago for some of the recent high school graduates. Okay, so this is d equal rt, and in algebra, typically r is the speed of the moving object, moving at a constant speed. So r is going to be d divided by t both sides. You get d over t. So that's exactly what this is. That's where I got that from. Okay, so velocity is d over t. Now let's actually measure the velocity. Now the distance that it travels, how do we find the distance? Because we need that distance, right? Well, let's see. This on the side here, if I look at tangent of theta, okay, tangent of theta, tangent of this angle, that's going to be 30 over d. And what is d here? Again, d is this distance right here. Let me label. That's the distance the truck travels in 1 second. That's what d is. Now from this, tan theta is opposite to adjacent. Now, notice it will be incorrect if you say that's 30 over 1. Just because it's a number doesn't mean that's the correct number. That's 1 second. It's not the measure of a distance. Okay. Now from this, if I this tangent, if I cross multiply this, what am I gonna get? Well, I'm gonna get d tangent, and theta is 15 degrees in part A, equal 30. So d is equal to 30 divided by tan 15. Okay, so notice how the angle actually helped us find the measure of the distance. And for this one, using your calculator, you get 111.96 feet. So we actually have now a tangible measure of a distance. That's not bad, right? So it's a good movement. In 1 second, it moved 120 feet. Okay, so what is the velocity then going to be? Let me move it here. The velocity is going to be d over t. The distance it traveled is 111.96 feet. And it traveled this in 1 second. So the answer to part A in feet per second the truck is going 111, almost 112 feet per second. Now, for me anyway, to get a feel for how fast that is in terms of miles per hour. So I'm going to go through some unit analysis here. And this is the way I set this up. This is clearly a fraction line, right, that I have. Now, first I'm going to convert feet to miles. Okay. Now, the way this works, if you have feet in the numerator, you cannot have feet in the numerator next to it for our unit conversion. You got to have feet on the opposite side of the fraction line. And the reason is because in a few moments, we're going to cross those out. The units actually cross out, just like the numbers do in a fraction. Okay, so this one is going to be 5,280 feet. And that's the conversion factor between feet and miles. 5,280 feet to a mile. Now, the other thing I have to, and you can see clearly here, I can cross out the feet, so I'm ending up with miles per second right now. Now, we need to convert from seconds to hours. Well, to each hour, there are 3,600 seconds, right? 60 minutes per hour and 60 seconds per minute. So there are 3,600 seconds in 1 hour. Now again, if I go like this, second and hour like that, see my seconds are on the same side of the fraction line, so they cannot cancel. I need to move them to the opposite side of the fraction, and so I'm going to go 3,600 seconds per 1 hour. I like working my unit analysis this way because I don't have to memorize, like, well, how do I know? Do I multiply by 3,600? Do I divide by 3,600? This way, the units actually tell me how I need to set these up. You see how the units, same units, must lie on the opposite side of the fraction line for them to cross out. And that's what I'm going to do. See, now I can cross them out. Let's see, once we cross these out, what's left over on the units? I have miles and I have hours, right? So this answer that we're going to get is going to be miles per hour, or simply MPH. We're familiar with that, miles per hour. And there I have it. And the answer that you get is about 76.3 miles per hour. So that's how fast the truck is moving. It was kind of fast for a truck, considering the mobility of a truck is limited. So that's a good haul. And there's the answer to part A. Got part A done. Now in part B, for part B, says if the angle measures 20 degrees, how fast the truck is traveling. Now, just kind of get a feel for this, whether the answer is going to be, is the truck going faster or slower? I'm going to move the truck about half the distance now. And this is the angle. Clearly, this angle that I have is greater than 15 degrees, right? Whatever that is, I know it's bigger than 15 degrees. So the greater the angle is to the road the truck makes with the highway patrol, the patrol's car, the greater this angle is, the smaller the truck is moving in that same amount of time, of course, right? In 1 second. Imagine if a second later the truck was over here. Look at that angle now. See this angle? This is now going to be less than 15 degrees. So in reference to 15 degrees then, it says if the angle is 20 degrees, I expect this answer to be smaller. In other words, the truck's going slower now. Let's do part B. So we need to again measure the distance it travels in 1 second. So I'm going to go tangent of theta. Again, it's going to be 30 over new distance, the new distance. And theta, we are told, is 20 degrees. So the new distance is 30 times tangent of 20 degrees. All right, and 30, 10, 20 degrees this time. I got, or sorry, hold up. When I cross multiply them, I get the new distance times 10, 30 is equal to 30. So actually the new distance I have to divide by. Glad I caught myself. Okay, 30 divided by 10 theta, and theta is 20 degrees now. So 30 divided by 10, 20. And this one, if I use my calculator, I get 82.4 feet. Notice it's going a smaller distance, right? Before it went 111.96 feet, and now it's going smaller distance. Well, in the same amount of time, in 1 second. And just to carry to 2 decimals, I got 82.42. So what is the velocity? The new velocity, I'm going to call it, for part B is 82.42 feet per 1 second. And my conversion factors are the same. To each mile, there are 5,280 feet. That will convert feet to miles. And 3,600 seconds per 1 hour. And that will convert my hours, seconds to hours. The seconds cross out, the feet cross out, and my answer is going to end up in miles per hour. And this time, so what you do is now you multiply 82.42 by 3,600. That answer divides by 5280. See the numbers that are on the same side of the fraction line multiply together, and ultimately divide the numerator by the denominator. And I just did. I got 56.2 miles per hour. Again, we knew that the speed's going to be lower now. Okay, so that handles part B. Now, in part C, if the speed limit is 55 miles per hour and a speeding ticket is issued for speeds 5 miles per hour or more over the limit, in other words, you have some flexibility. You can go up to, in a 55 mile, you can go up to 60 and they say, yeah, that's fine, close, that's okay. And beyond that, you get, let's say, a citation. So really, to get ticketed, you have to do more than 60 miles an hour according to part C. Now we want to know, for what angles should the trooper issue a ticket? So we want to find a measure of the angles here, right? So in part C, if the velocity is greater than or equal to 55 plus 5, that's greater or equal 60 miles per hour, then a citation is issued, correct? All right. Now, let's see, we need to convert this into miles per hour. Okay, so how do we convert it into miles per hour? So we're going to do it kind of like we did in parts A and B, right? We need to convert these. So that means if the velocity is greater than or equal to, in terms of feet per second, I'm going to do 60. Now check this, how this is going to work out. Now we want to convert from mile per hour into feet per second, because the distance is given in feet, right? In order to find the measure of angle theta, I got to have this adjacent side in feet. So remember, miles, same units go on opposite side of the fraction line. This time I do 5280 feet per mile. The miles this way get crossed out, and I have 1 hour. I put hour, see, I have hour in the bottom. So I'm going to put hour in the numerator, and to each hour there are 3,600 seconds. So this would be the conversion factor. You see that now I can cross hours and I can cross miles, the final answer is going to be in feet per second, which is what I want. And in terms of feet per second, now this turns out to be 60 times 5280 divided by 3600. And you get 88 feet per second. Okay, 88 feet per second. Now, velocity is change in distance per unit of time. For these exceeding 88 feet per second, the citation is issued. And then we need to, let's see, convert in terms of angle theta. Okay, let's see how this is going to work. T is 1 second, right? We know this is 1 second. So I'm going to multiply both sides by 1. So D is greater than or equal to 88 because T is 1 for this exercise. All right. Now, remember the distance. We did it up here. Distance is 30 over tangent of the angle, right? In both cases. D is 30 divided by tan of theta. So I'm going to put 30 divided by tangent of theta must be at least 88 to get the citation. Now if I multiply both sides here by tan theta, and because it's a positive measure, see the ratio is positive 88. So that means tan theta has to be positive, and I'm multiplying both sides by tan theta, so I don't need to change the direction of my inequality. That's 88 tan theta, and divide both sides by 88. So as long as tan theta is less than or equal to that ratio, the patrol can give a citation. Now in terms of the angle, therefore theta is going to be, for theta less than or equal to the arctangent of 30 over 88, right? It's gonna have a citation. So theta is going to be 18.8 degrees. Any angle less than or equal to 18.8, that means that the truck is going at least 60 miles an hour. Okay, and there we have it. I think we've done enough examples for this section. Again, the right triangle trigonometry, the applications are very versatile and very practical. And with that, we are done with this video. Again, thank you for watching, and hope to have you in another video, another lecture.